This first problem asks us to provide R or S labels for these structures. We need to prioritize the substituents coming off of the chiral centers, and the procedure for doing that is described in the previous video. The video, these three examples, is provided in the wedge and hash line formation. In a case like this, where the fourth priority substituent is neither towards us nor away from us, we can't simply count 1, 2, 3 or 3, 2, 1. We need to reorient the molecule, and one way to do that is to use the stick figure representation, drawing an analogy between the molecule's handedness and the handedness of a person. And if we imagine a person doing push-ups with their feet towards the right and their head up here towards the left, and the person's right hand and the person's left hand, like this, we can easily redraw this. And I would recommend redrawing it as a Fischer projection with the head at the top. That was an ethyl group, which was the fourth priority. The right hand, if someone's looking at you, would be over here. That's the first priority. Left hand would be the second priority. And the feet, as drawn here, would be the third priority. And now, since the Fischer projection by convention represents a structure where the vertical groups are pointed away from you, now your lowest priority, fourth priority substituent is away from you, and you can count 1 to 2 to 3. That goes in a clockwise fashion. That's the R isomer. If we move over to the second example, it's already in a Fischer projection. Our lowest priority substituent, number 4, is already pointed away from us. We can just count 1 to 2 to 3 and see that is also in the R configuration. There are several ways to deal with stereochemical assignments for a Newman projection, as in structure 3 here. And I'll show you just one of those ways. If we've labeled these substituents 1, 2, 3, 4 already, we might choose to view the molecule and redraw it so that we're looking from this side, so that the fourth priority substituent is pointed away from us. So if we take a look at a three-dimensional model of this compound, and this molecule on the right side of the screen is the molecule we started with, and I built it over here with a CH3 in the front. This red atom is the bromine. There's an ethyl group coming at the top on the back atom over here, and then over we have this fourth position on this H, and that's here. And we can turn it and see that if we're looking from this perspective, we want this H to be pointed away from us. That's this H in the back in the three-dimensional drawing. I can rotate that and show you what it would look like. It looks like this now. And that H right here, we've rotated so it's directly behind our line of sight, just like it would be in this line of sight we've chosen in the drawing. So I've reproduced this molecular model here, and now we see that our first priority bromine is here, our second priority ethyl group is here, and our third priority, the whole front carbon, this CH3 unit on the Newman projection, is here. And since the fourth priority is now pointed away from us in our new perspective, we can go 1 to 2 to 3 in this way, and that would be an R isomer. The next type of problem is to draw each compound as a Fischer projection. And regardless of which wedge and hash line structure you had on your worksheet, the strategy that one would use is probably to use the imagination of the person doing push-ups with feet here, head here. In that perspective, the hand coming towards you would be the right hand, and this unit going away from you would correspond to the left hand. A Fischer projection is, by definition, a perspective looking like this, with the horizontal coming towards you and the vertical going away from you. If we stand this individual up, the face would be here, the feet would be here, and the hands would be here. This would be the person's right hand if they're facing you, and this would be the person's left hand if they're facing you. So if we look at the molecule from this perspective, where you're looking so the hands are coming towards you, you can very easily draw the Fischer projection, where the head, as we're imagining this, is the CH3. The feet, the bottom part, is an ethyl group. The group we're imagining is the right hand is fluorine. Again, if the person's looking at you, their right hand is on your left, and on the left hand of that individual would be OH. So that's a proper Fischer projection for that molecule. So again, I've built a model where you can have a molecular model kit and build this. I've used a computer program where the chlorine is at the bottom. So here's your chlorine, the green. 2 hydrogens over here, one in the front pointing up, that's this one. One on the back carbon pointing down. The back carbon is hidden behind the circle in the Newman projection drawing. I have a CH3 on the back carbon coming out from behind the circle. That's right here, CH3. And then coming out at the top on the back carbon is an OH, and that's this red oxygen, and the white is a hydrogen. And that's coming off the back carbon. So it looks like this. Now a Fischer projection, we can rotate this any way we wish, but the Fischer projection has the 2 horizontal groups coming towards us. So if I go over and try to draw this, I could draw in my scaffold, and I would say I have a CH3 group coming towards me on this side. So I could fill that in over here. I have this CH2 with a chlorine would be on this side. So go back over here, CH2 with a chlorine. At the top, going away from us in the Fischer projection, is the OH. You can fill that in here. And then going down here, there's a hydrogen. Now there are plenty of other correct ways to do this. We could have rotated this in any way. If we go back to the original perspective with the chlorine at the bottom and the oxygen at the top, we could have rotated it the other way so that the hydrogen would be over to one side, as long as the horizontal groups are coming towards you and the vertical groups are going away from you. Right? And going back to the original, we could have even rotated it a different way so that the hydrogen was at the top, and then these would be the horizontal or the arms of the drawing here. So there are many different perspectives that you could have used to draw this, depending upon what vantage point you chose to look at this from. The last type of problem in this problem set was one in which we were trying to identify the relationship between any 2 given molecules amongst this set. And the trick here is to know that enantiomers are mirror images of one another. If you take a stereocenter and you reflect it in the mirror, a left-handed molecule will become a right-handed molecule and vice versa. So when you look at the stereocenters in these molecules, in order for a molecule to be an enantiomer of this first one, let's call it A, you need to switch the configuration about both stereocenters. So if both of those, which start off having the bromine or chlorine on wedges, switch to being hashes, that's an example of an enantiomer. Same thing for these molecules on the right. Let's call these molecules X and Y. If I have a hash line on bromine and it switches to a wedge, that's what a mirror would do. It would switch the configuration. Likewise for the chlorine, it switches from a wedge to a hash. You've switched the configuration of both stereocenters, so those 2 are also enantiomers of one another. If we take a look at a different type of relationship, let's say between X and B, you see that one of the stereocenters, the bromine, maintains the same configuration in both molecules, but the configuration at the carbon with the chlorine on it changes from this hash line to a wedge. So you've changed the configuration of one stereocenter but not the other. So they're certainly not identical because you've changed this configuration at one site, but they're also not mirror images because you didn't reflect both of the configurations and invert those. That's an example where you have a diastereomeric pair. And then if we compare A to Y, also those are diastereomers. You've switched one configuration, in this case the chlorine versus this chlorine, but you didn't switch the configuration at the bromine when you compare those 2. You can also compare A to X. In that case, you've switched the bromine, but you haven't switched the chlorine. Configuration of the bromine carbon, configuration of the chlorine carbon. So those are diastereomers as well. And finally, if you compare B to Y, you've kept the configuration at the carbon with the chlorine the same, but the configuration at the carbon with the bromine on it has changed. It's a hash line here, it's a wedge here. So those are also diastereomers.